Alright, so today we're covering semi-simple Lie algebras. I gotta see how this recording session is gonna go, but this might end up being a bit of a shorter episode just based on how we gotta pace things in the future. So, and just a quick reminder, our setup here, we're doing everything with finite dimensional Lie algebras, and everything's gonna be over a field of characteristics 0. I think we had that set up like last time. Just a reminder, we're carrying on with that. So, we ought to start with a definition, right? As you do when you're introducing a topic in math. Definition. A Lie algebra, we'll call it G, is semi-simple if its only commutative ideal is the trivial one, which is just 0. Remarks. So the zero-dimensional algebra is obviously semi-simple. And it says there are no semi-simple algebras of dimension 1 or 2. But there are some of dimension 3. I guess I should be writing things a bit slower since we're gonna maybe have to stretch things out. We also see that a semi-simple algebra has 0 center and thus its adjoint representation is going to be faithful, which, if you recall, just means that it is injective. So essentially we get all of the structure of the algebra on the representation, and this is easy to see. And the center commutes everything, so its adjoint is just going to be 0. Since every non-zero element in a semi-simple algebra is going to have a non-zero center, a non-zero adjoint representation, so it's faithful. So, and of course we have a collection of semi-simple Lie algebras then their product is also going to be semi-simple. As if A and G is a commutative ideal, then the projection of A onto each Gi is going to be a commutative ideal in each Gi, and therefore is going to be 0 for all I. So A is just 0. So G is semisimple. Alright. Now we get a theorem which gives us some equivalent definitions of equivalent conditions, I should say, for semisimplicity. So we're going to let G be a Lie algebra. I guess I should write everything out here. Let G be a Lie algebra. Then, as always, we get the following are equivalents. So we're going to get some equivalent definitions for semisimplicity, as I said. The first one, of course, being that just G is semisimple, which I'm going to write it out explicitly. We had above that no non-trivial commutative ideals. Condition B is that the radical R of G is 0. Condition C states that the killing form beta of G is non-degenerate. Which I think is going to tie back to the fact that the adjoint representation of a semisimple algebra is faithful. But I mean, I guess I should let the text explain that. And we note, I guess we'll just say also to introduce this. G, also note that a semisimple algebra, which is going to be G, is equal to its derived algebra. Now let's look at the proof of these equivalencies. First off, why does A imply B? If R is, on the other hand, non-trivial, then the last non-zero derived algebra of R is a commutative ideal of G. So essentially we're showing the contrapositive of A implies B, showing that if the radical is non-zero, we can construct a non-trivial commutative ideal of G. Condition C we have already shown this one here in a previous video. And C implies A was also a proposition we've shown. And they don't even discuss this last part, but oh no, it follows from some of the versions. Yeah, okay, never mind. So that's our theorem there. And it comes, of course, with a corollary, which states we're going to let G be a semisimple Lie algebra and it's going to come with a representation of rho on a finite dimensional vector space V. Then we have that the image of G under rho, the representation of every element of G, is a special linear function on V, element in a special linear Lie algebra. And our proof the linear form which sends x to the trace of the representation of x. Because keep in mind, representation, well, essentially is sending it to the general linear Lie algebra of V is 0 when x is of the form y bracket z, which is, because then you can show that the trace of a bracket, the adjoint of a bracket, is going to be 0, which means the trace is 0 on the derived algebra of G, but we have from above that that is just all of G when G is semisimple, and so the trace is always going to be 0. I have a proposition here. Let G be a semisimple Lie algebra and rho a finite dimensional faithful representation of G. Faithful representation of G. Then the bilinear form associated. And so it's bilinear form on G associated with rho, our representation, is non-degenerate. So we saw from before that the killing form is non-degenerate, is equivalent to saying is equivalent to semisimplicity, And this is just kind of that the version of the killing form on a representation is going to be non-degenerate as long as that representation is faithful. And the proof is pretty easy. The orthogonal of G with respect to this form is a solvable ideal and hence is going to be 0. Now let's look at the corollary of this. Let G be a Lie algebra beta its killing form and A is going to be A is a semisimple subalgebra. It's always fun trying to form sentences when they use A as a variable. Semisimple subalgebra of G. The orthogonal H of A with respect to the killing form is a supplementary subspace. Supplementary subspace of A and G, of A in G, and the bracket of A and H, the image of the adjoint of anything in A, the G adjoint of A and on anything in H is going to be inside of H, or vice versa, I guess. If A is an ideal of G, so is H. Which is then the centralizer of A in G. Alright, in this one we are going to have a proper proof of, which we're going to start here. We're going to let beta prime be the restriction of the killing form to A. Is the bilinear form associated with the representation, and this representation is going to send an element x to the G adjoint of x, as you'd expect. And this is going to be of the elements of A on the space of G, of course, even though this is the G adjoint. This representation is faithful, given that our A is assumed to be semisimple as a subalgebra. It's faithful, and hence our representation here, which we recall is denoted to be beta prime, is non-degenerate. Hence H is supplementary to A in G. All right. Now if we have two elements, we're going to pick two elements of A, call them x and y in A, and z is in H. Then the killing form of x and the bracket of y and z is equal to the killing form of the bracket of x and y and z, which is going to be equal to 0. Since that the bracket of x and y is an A, since it is a subalgebra, and hence the bracket of y and z must be within H. So that the bracket, keep in mind that y is arbitrary in A and z is arbitrary in H, and this bracket is always going to end up then inside of H. If A is an ideal of G, we know that its orthogonal is going to be an ideal. H is ideal of G. And that G is identified with the direct product of A and H, as the center of A is 0, the centralizer in G of A is H. And that's all of our little consequences we had there. There's two corollaries. First one states every extension of a semi-simple Lie algebra by a semi-simple Lie algebra is both semi-simple and it has to be a trivial extension. And this is just follows immediately from what we have above, because we can set our extension, I believe, as A, base is H, and we get that G is identified with A cross H, and so then, yeah, I believe. So we have another corollary, which is going to end off the episode. I mean, it's been almost half an hour. It's almost an episode. Kind of. We can pass off, maybe. Last corollary states that if G is semi-simple, every derivation of G is inner. And the proof we have seen that the adjoint representation of G is obviously is going to be isomorphic to G, since that every non-trivial representation is going to be faithful. Well, we know that the adjoint representation is going to be faithful, and it's obviously going to be invertible. So I guess maybe I should write this out. The adjoint representation of G is, in this case, isomorphic to G. You know, non-trivial, we have a trivial center. And so hence the adjoint of G is semi-simple itself, and an ideal of the derivations of G, which, if we recall, is in fact a Lie algebra, with the bracket being xy minus yx, as you'd expect. So if we have a derivation D in the derivations of G commutes with the elements of the adjoint representation of G, then for all x in G we have that the adjoint of the derivation of x is going to be equal to the bracket of d, and the adjoint of x, keep in mind d of x is in g, so the adjoint of d of x is going to be in the derivations of g. And so this bracket, both of these, d and the adjoint of x, are derivations, so this bracket is happening in the derivation of g. If they commute, then this is 0. So the adjoint representation of d of x is 0, but we know that it's faithful, so d of x has to equal 0. But x is arbitrary, so the derivation d has to equal 0. Thus it follows, thus by previous corollary. And do we end it here? Yeah. Semi-simplicity of representations is our next topic. It's probably going to be super long to make up for this, so look forward to that. I guess we'll call it here.